my job today is to talk about some of the contributions that folks from the Bloom Center and other folks that have made in this topic of earthquake resilience of transportation systems. So, as with many aspects of earthquake engineering, a lot of the research has been informed by the lessons that we've learned after earthquakes, and these have contributed to the advancement of bridge seismic design practice. We started designing bridges for seismic loads as early as I believe in the 1940s, but it wasn't until the 1971 San Fernando earthquake that we started seeing significant changes in bridge seismic design practice. And following that, with each subsequent event, we started learning very specific lessons about how to better design and retrofit bridges for seismic performance. So as those lessons were being learned based on those field investigations, at the same time, there was a lot of research that was going on, both analytical and experimental, to advance seismic design and performance assessment of bridges. So this figure here is from work done by Professor Doran Lehman and Jack Maley, where they started thinking about implementing performance-based principles in the design of bridges. And cumulative damage of bridges, that's something that we as a community, we started thinking about as early as in the 1990s, and we continue to think of it a lot today because it has a lot of implications to the functionality of not just bridges, but transportation networks in general. And so a lot of that research has both informed and been informed by a lot of the guidelines that have been developed over the years. So for example, this ATC 6 guideline that was published in 1981 for the seismic design of bridges. There was a follow-up one that focused on seismic retrofit, and these guidelines continue to be evolved over the years. This most recent one is the most recent release of the Caltrans seismic design criteria, and it cites a lot of the work that was mentioned on the previous slide related to the design and performance of bridges. So one of the things we learned both from the Loma Prieta and the Northridge earthquake is that damage to bridges, you can have consequences that can propagate throughout the transportation network. And so we started to think about ways that we can develop these large-scale simulation models to manage the risk to these transportation networks. And to give you a sense of the scale of the problem, for the Bay Area Bridge Network, we have more than 4,500 bridges, and these are connected by a road network where you have more than 32,000 segments and accommodating more than 20 million trips per day. And there are other types of modes of transportation. There are other modes of transportation that facilitate millions of trips per day. So very early on, Professor Anne Kermijan and Nisreen Bassaz, they did a study looking at data from the Loma Prieta and the Northridge earthquake. And the idea here was to do a data-driven investigation of the damage during these two earthquakes. I have one particular finding from that study that I thought was interesting. I know there are a few people in the room that are developing these large-scale simulation models for bridge networks, and I think it's a single number, but I think it's a good number that can be used to sort of ground our models in some sort of reality, where it says less than 5% of the bridges exposed to ground shaking were damaged. So that's something we can keep in mind. And so this study was published as part of a MCA report, and it also provided very important information on the types of bridges that were more susceptible to damage, right? And ultimately, they also used that data to develop fragility curves that were implemented in HAZUS, which is widely used even till today. Later on, Professor Kermijan and her colleagues started, they basically pioneered these large-scale transportation models that looked at not just different types of seismic hazard, but bringing together the inventory of the network, as well as the operations, the transportation operations that are built within that network, to quantify risk, not just in terms of repair costs and physical losses, but also in terms of operational loss, things like accessibility delays and things like that. Again, building on that, Jack Baker and his team started looking at these transportation systems, but instead of looking at just a single or a few scenarios, they started looking at thousands of scenarios. So this slide is based on some work by Mahalia Miller, and so they developed this 4-step process that starts with characterizing the ground motion intensity map for those sets of scenarios, and ends with assessing impacts at the community level. And by using these stochastic event sets as the input for these types of assessment, you can start to characterize these community impacts in terms of some annual rate of exceedance, or you can look at some period of time and some performance metric and try to quantify the probability of exceeding or meeting some performance metric within some period of time. Now, when you start doing these regional risk assessments and looking at these large sets of scenarios, it starts to get computationally expensive. So one of the things that Mahalia and Jack looked at was, developing a procedure that allowed you to select a subset of the ground motion maps and use them for your risk assessments, such that the final result you would get would reflect the performance that you would get from the full set. And this is actually some work that they did that built on some earlier work done by Rachel Davidson and her group, another Bloom Center alumni. Again, Jack and his team continue to build on that work. This is some work from Rodrigo Silva Lopez. He was thinking particularly about developing optimization algorithms to be able to prioritize the retrofit of bridges within a network. And in doing so, they thought about considering socio-economic disparities in the earthquake impacts. And one of the things that came out of that was that if you want to inform policies that reduce risk in an equitable manner, then you have to disaggregate the losses based on income and other types of socioeconomic metrics. Okay, so starting to think about, so Abby mentioned earlier, or was talking earlier, about functional recovery of bridges. And so there's a national push that's happening there of building, and at the same time, a lot of the same activity was happening for Lifeline. So this is a NIST publication, NIST report that was led by Aisha Hortatsu, another Bloom Center alum, and we had some other participants from the Bloom Center, Anne Kermijan, Farzeen Zarian. And the idea here was to develop an initial framework to design Lifeline infrastructure for functional recovery. Now, this figure shows an overview of the framework that they came up with. It's somewhat complex, but there's two things I want to point out. The first is that they highlighted the importance of looking at the components of the system and how those components serve the basic intended functions of the system. And the other thing was they highlighted the importance of organizational actions in functional recovery. So the level of preparedness of the organization and different types of interventions that can be done after the event to enhance the functional recovery. So with that in mind, my group at UCLA, we've been working to develop a framework for modeling post-earthquake functional recovery of bridges. And as we started this work, so we started this work at a time when there was a lot of work already done for buildings in the functional recovery space. So we started to think about, okay, when you think about buildings and bridges, what are some of the ways that the thinking in terms of functional recovery would have to be different? So for example, the ownership structure is different, right? So buildings are generally owned by homeowners, businesses, and the repair efforts tend to be very centralized, whereas with bridges, they're owned by transportation agencies and the repair efforts are generally more centralized. The way you define recovery states for buildings and the way you define disruption for buildings is different for bridges. So that's something that we had to think carefully about. And then the financing, which is an important part of the post-earthquake recovery because these repairs have to be financed. That's another thing that's different when you think about buildings versus bridges. So that's not good. So, some of the things we had to think carefully about was how do you go from the physical damage of the bridge to thinking about the functionality states of the bridge, right? So we had to think carefully about that. And then what are the impeding factors that are applicable to bridges and how are those impeding factors structured? And then the sequencing of repairs of the different components that made up the bridge, that was also an important consideration. And because a lot of that is based on decisions made by the organization that manage these bridges, we spent a lot of time talking to folks at Caltrans, as well as practicing engineers and builders from private organizations to help inform some of this. And so, this is starting to get a little bit messy, but here I'm showing just highlighting some of the complexity associated with just the impeding factors themselves, some of the issues related to the sequencing that you need to consider for the repairs of components, and then some of the types of results that you would get. So you would get something like, the probably distribution of the functionality states. You can get information on which impeding factors dominate the recovery, as well as which component repairs also dominate recovery, and then also quantitative information on the recovery time distribution. And so what we're doing now is trying to scale that up at the regional level and think about different types of interventions. So interventions that range from retrofit of bridges or interventions related to after the event, like in increasing the workforce and thinking about how those can improve the resilience at the network scale. Now, as we start thinking about scaling up about doing these high resolution simulations for these regional assessments, we can start to reflect on how we've advanced the vulnerability characterization of bridges over the years. So, for example, the earlier studies that I mentioned that did these bridge network risk assessments use the hazards fragility curves that are defined at the system level. So you can think of these as sort of low definition, low fidelity bridge definition, because we're not really getting any information on the impact to the various components. The functional recovery methodology that I mentioned earlier, we actually used component level fragility. So this is based on a lot of work that was done by Reggie DeRoche, Jamie Paget, and others by Rice, at Rice, where you're starting to get more higher fidelity information in terms of the components that are impacted and what types of repairs and things that are going to be needed. But we also have folks that are starting to think about, okay, can we do these regional assessments using high fidelity simulation? And so, for example, there's some work that's going on right now in Greg Dearline's group where they're trying to do these regional assessments. So they're trying to scale things up, but they're trying to maintain the type of fidelity that you would typically have for bridge-specific assessment. And so what they're doing is they're using these surrogate models to try to make this process computationally feasible, right? So essentially what these surrogate models do is they would take in information about the site, about the bridge, different ground motion parameters, and they would give you quantitative estimates of impacts in a similar manner that you would get from if you were doing a detailed structural analysis. And the benefit there is that once you have these surrogate models trained, you would significantly reduce the computational time that's needed to do these types of assessments. This slide is based on some work that's ongoing, that's being done by Farzin Zarian at UC Irvine. He's actually working very closely with Caltrans, trying to enable performance-based design of California bridges. So what Farzin and his group are doing is they're doing a large number of parametric nonlinear response and damage analyses. And what that would allow is when a Caltrans engineer does a design, they can actually get information about the likely level of damage that can be used to infer repair costs and functional recovery, as I mentioned earlier. So as we think about sort of future research, I thought I would reflect on this study, this National Academy study that I had an opportunity to participate in, where the focus was trying to give transportation agencies throughout the country state-of-the-art information that can be used to help make decisions about investing in transportation resilience. And so as we started this effort off, one of the things we had to acknowledge was that when it comes to these investments, the leaders of these agencies, they have really tough choices to make about where to invest their dollars, right? Because usually there are a lot of different issues that are going on, and so these are really tough decisions. So one of the things that sort of permeated this effort was the need for a cost-benefit based decision support system, right? And as we think about strategies for enhancing resilience, one of the things that came out was that we need to be thinking about strategies that could both limit damage, but also think about strategies that can be implemented after the event, because oftentimes from a cost effectiveness standpoint, it's those post-event strategies that end up being more cost effective and realistic to implement. Another lesson that we learned from talking with a number of different transportation agencies throughout the country is that a lot of the models that have been developed in research do not make their way into practice. And part of that is just lack of awareness, but part of it has to do with sometimes the model complexity. And one of the challenges is if you have a model that's developed for a single mode of transportation or say a decision support system that's developed for a single mode of transportation, from a cost effectiveness standpoint, it's harder to justify use. So there needs to be work done across different modes of transportation. And so with that in mind, one of the recommendations that came out was engagement with end users earlier in the model development process. So maybe even as early as the model conceptualization stage. So I'll end with this slide. So this should say, here. So I guess the E fell off the cliff there. So this is my last slide. So this slide shows the so-called V2X network, so vehicle to everything connection. And as we sort of move forward into the future, vehicles are starting to be more and more connected and rely on these digital communication systems. And one of the nodes is in that network, or several of the nodes in that network are infrastructure systems, right? So that's the V2I edge that you're seeing there. So what the implication of this is that now the infrastructure, when you think about an earthquake and the type of disruption that it can cause, now you can have the damage that propagates now within the communication system, and this has to be considered in the future in the risk models that we're developing in the future. Thank you.